So we're going to look at a variety of these limits at infinity, and I'm going to go kind of rapid fire here, but we've got some variation in here that we do need to discuss a little bit. So in this first example, we've got sine of x involved here. So this is the first trig function that we've seen, and what we know about sine of x as x gets really big is that it's going to oscillate, it's going to go up and down, but it is going to be bounded by -1 and +1. So even though sine of x is not approaching any particular value, if we were just looking at the limit of sine of x as x approaches infinity, that limit itself would not exist. But in this particular example, what matters is that the numerator is going to be some finite number between -1 and +1. In the denominator, we've got an expression that's going to be dominated by the x squared, which is going to go to infinity. And so what we have here is a bounded number on top divided by an infinite number on the bottom, and that's going to give us a limit of 0. Our next example here is kind of similar. Difference here is that we have that e to the x times sine of x in there. So I'm going to start with this inequality that I just had and multiply all three parts by e to the x. Now, e to the x is a positive number, so my inequality is not going to flip. So what I know is this top here is going to oscillate just like the sine function oscillates, except it's going to oscillate instead of between -1 and +1, it's going to oscillate between negative e to the x and e to the x, which means as x gets really big, this is going to be a really big negative number, and this is going to be a really big positive number. So what we need to keep in mind here is it's not approaching some particular number, so that limit also doesn't exist, but also the swings are going to be getting bigger and bigger and bigger as x gets bigger. Now the denominator again is dominated by x squared, which is also approaching infinity. So what we've got happening here though is the top is going to be dominated by that e to the x. So it's e to the x times sine of x, but we're going to be getting values that are getting as big as e to the x, depending on the x values. So because that e to the x is dominating the top and the x squared is dominating the bottom, the e to the x is going to have a greater impact, and this limit is not going to exist. So the values that we get as we plug in bigger and bigger values of x are going to fluctuate between positive e to the x and negative e to the x. And so this is going to diverge. It's not going to exist. Okay, now this one is interesting. The difference here is that we're going to negative infinity. So as we go to negative infinity, let me throw that inequality that I had up here. As we go to negative infinity, e to the x is going to actually approach 0. And so both of these are going to approach 0. And if you remember the squeeze theorem, if we have two limits that are approaching 0 and another function squeezed in between them, that means that the numerator here is also going to be approaching 0. So remember e to the x, if x is a negative number, so I'm going to just write e to the negative k here is the same thing as 1 over e to the k. So when we have a really big negative number here, this is going to be a really big exponent here, and that is going to go to 0 because we have 1 divided by a really big number. Now, on top, we're going to be approaching 0. On the bottom, we're going to be approaching infinity. That x squared is still dominating the bottom, and 0 divided by anything is 0 besides 0. If it's 0 over 0, we have an indeterminate form that we have to do stuff with. But 0 divided by any constant is going to be 0. 0 divided by a really big number is also going to be 0. So this limit is 0. Okay, now we've got that e to the x in the denominator. So this one's going to be a little bit different. We've got to kind of think about what's going to happen here. Remember, this expression right here is going to be between the opposite of e to the x and e to the x. All right, but what's important here is it's between these two. These two are getting farther and farther apart from each other. So if we looked at the graph of those two, e to the x is here and negative e to the x is here, and the sine function then is going to be oscillating between those two. So the value that we're getting in the denominator, it's getting really big sometimes, and it's getting really big negative sometimes, but it's also zero sometimes. And it's also kind of small positive numbers or small negative numbers sometimes. So when we're dividing by numbers in the denominator that are not approaching any particular value, then we're dividing sometimes by really big numbers and getting really small numbers, sometimes divided by really small numbers and getting really big numbers. And so it's not going to be approaching any particular value. So as the top approaches infinity and as the bottom oscillates, then we're going to have an oscillating function here, and this limit is not going to exist. Okay, this one's a little more straightforward here. So the top is dominated by the 2 to the x. Sorry, let me just circle that. So remember, the exponential functions grow faster than the log functions, so that log function is going to be negligible in the long run. The denominator is going to be dominated by the e to the x. Sine is going to be confined to a range of -1 to 1. So this is going to behave like the function 2 to the x over e to the x as x gets really big. Now, these are both exponential functions. If one was exponential and one was a polynomial, then we could say one dominates the other. Since they're both exponential, we can't really say one dominates the other. Now, the e to the x is going to grow faster, but we need to know really how much faster. So what I'm going to do is I'm going to use a little algebra here, and I'm going to rewrite this. So I'm going to rewrite it as 2 over e, and then that quantity raised to the x power. So by doing that, we can think a little bit more about what happens to this function as x gets really big. And what we need to know to answer that is about what e is. Remember, e is in the 2.7 range. Okay, it's got more digits after that. The important thing, though, is that e is bigger than 2. So what we've got here is a number that is less than 1 and raised to a big power. All right, so if you could kind of experiment with this on a calculator, but if you take any number less than 1 and you raise it to a big power, it's going to get closer and closer and closer to 0. So this limit here is going to be 0 because of that property. Okay, some square root problems. So this one here is going to be dominated. The numerator is going to be dominated by the x to the 5th in the square root. The denominator is going to be dominated by the x squared. So this is going to behave like the square root of x to the 5th over x squared. Now remember, square roots can be written as an exponent as a 1/2 power. So this is the same thing as x to the 5 halves. And so this whole expression here simplifies to it's going to be x to the 1/2 or the square root of x. So if we plug in really, really big numbers for x, the square root of x is also going to get really big, just not as fast. So this is going to be an infinite limit. The bottom one here is interesting, and we have to be careful about this. Since x is approaching -infinity, we have to think about what happens when we plug in a negative number for x. And there are some negative numbers here that would make this expression positive, maybe. I'm not really sure. But if I plug in a really big negative number in the numerator and it's dominated by that x to the 5th, that's going to be a really big negative number. And when we try to take the square root of a negative, we get imaginary numbers. So big negative numbers are not even in the domain of this function, which means this limit is not going to exist. Okay, so if we were to graph this function, we wouldn't even have a graph for large negative numbers for x. Got a variety of other square root ones. I do want to point out that all 4 of these have x to an even power inside the square root. So even when x is approaching -infinity, we're not going to have that domain issue like we did in the last problem. So let's just kind of look real quick at dominance here. So the denominator is going to be dominated by the square root of 9x to the fourth, which is 3x squared. X is a positive number, so we get a positive 4x squared divided by a positive 3x squared, which is going to be 4/3. Looking at the same one as x approaches a negative large number, what's going to happen here when we plug a negative in for x and then raise it to the fourth power, we get a positive. So in the denominator, this is approaching 3x squared, but it's going to be positive values. And then the numerator, we plug in a negative number for x, we also get a positive. So that's 4x squared. We have a positive divided by a positive, still going to be 4/3. Okay, so our horizontal asymptote going to the right and our horizontal asymptote going to the left are actually going to be the same value. Now over here, numerator dominated by the square root of 36x to the sixth, that's going to be 3x cubed. And denominator dominated by 2x cubed. X is a positive large number, so plug in a positive number for x here, we get a positive square root, we get a positive values in here for x, positive divided by positive, it's going to give us 6 divided by 2, which is 3. All right, so this one right here is going to be a little bit different. This is where we have to be careful about the negative values for x. So we plug a negative in for x here, raise it to the sixth power, we get a positive, and then we take the square root of that, we get a positive. So this is going to be 6x cubed, like I wrote up here, except since x is approaching a negative number and we know this is positive, it's actually the absolute value of 6x cubed. And that's true on this one up here also. We just didn't need to say it because we're dealing with positive numbers. So in the denominator, we have 2x cubed dominating. I don't really need to write that again. But that's going to be a negative value because x is a negative number. So a negative to the third power is going to be negative, which means that we have a positive 6 on top and a negative 2 on the bottom, and that's going to give us a limit of -3.